Hello, today we're going to embark upon a reverse engineering project. We have a B&K Precision triple output power supply right here, and it was pulled out of the trash can. Apparently it needs some repairs. It was deemed not worth repairing, so we have it on the bench today. Our objectives are to see, how does it work and can we fix it. Before we even start taking it apart, it would be a good idea to see how does this thing work. Is it really broken, or how badly is it broken? So we'll plug the cord into a power strip that has a fuse in it or a circuit breaker. That way, if it's shorted out, it's not going to blow the circuit in the building. So it's always a good thing to do. And now we'll try to turn it on. And it's turning on. You can hear the fan came up. There are voltages and numbers appearing on the screens right here. So what this instrument does is it provides an output voltage. There's 3 different voltages, and they're adjustable. I can turn the knob right here. And so that's saying I'm putting out 20.9 volts on these terminals right here. I could limit the amount of current that goes to those terminals. Right now it's showing 0 because there's no load across there. If I short-circuited those, which I could do, then all of a sudden there'd be current flowing. Now the other side, if I turn the knob here, like, oh, it's kind of acting strange, right? It's going from like 0 to 50 volts, and I know this power supply is only good up to about 30 volts, so maybe there's a problem. There's current flowing. So I'm guessing that this channel right here is bad. So the channel 2 of the power supply is bad. So that's going to give us a little bit of insight into what we should look at next. Reverse engineering or repairing electrical instruments, you need to have voltmeters. So these are 2 examples right here. Then there's a 3rd example. So we have a voltmeter over here, which is in a rack, and then there's an oscilloscope. So oscilloscope is an instrument that measures voltage versus time on the screen. So if we had an AC waveform, like a sinusoidal type of waveform, we'd be able to see it on there. So the power supply that we're working with today is a DC power supply. So we're expecting to have DC voltages appearing at the output terminals right there. So first thing we want to do is turn it on and see, is it actually providing output on our broken channel. So we connect our multimeter common to the negative terminal, and then we connect the high voltage or the V plus terminal on the voltmeter to the positive terminal with the banana plugs. And when we do that, we see that our meters are in agreement right here. 49.4 volts, 49.4 volts over here, meaning that this meter display is working, but somehow this voltage control isn't working right there. And same thing, it goes to 0 there, almost goes to 0 on that one. So we're starting to get a little bit of a sense of the problem here. So another thing we might want to do is see, is there any AC voltage appearing across this terminals right here? And if we switch the meter to measure AC voltage, we could see there is virtually 0. So it's saying 0.6 millivolts AC, which is in the noise floor, meaning that our DC power supply is putting out DC. Let's see if that holds here. Yeah, it does hold here. So even at 49 volts DC, our AC component's very small. So it is working as a power supply, it's just unable to control its voltages properly. In other words, when we turn the knob, instead of seeing the smooth varying voltages that we see when we turn this knob, it's jumping around. So now it's probably time to get into the instrument and see what's going on. So before we open anything up, we always turn it off and unplug it. So we turn it off. And I usually unplug things from the instrument if I can. And if you go to the back of this particular instrument, the power cord's removable. So if I pull the power cord out, I know that it's completely it doesn't have any connection to the power anymore.